Hi, everyone. I'm here with Alejandro Daniel Noel. Great to have you on the podcast. As usual, I'll start with a short intro on your background. You got your master's from TU Delft, working with Active Inference and the free energy principle. And you are now a full-time software engineer at Google, specializing in machine learning engineering for conversational AI. So the two research areas you have focused on naturally give us two larger topic blocks to talk about. Active Inference and language models both are really complex and fascinating topics at the forefront of very interesting developments, both in neuroscience and AI, and the intersection of the two. But given the scope of these topics and our shared interests in all things related to intelligence, I expect there will be many interesting diversions down the road that we can take. To start things off, we can just jump in a very general sense with a question of what fascinates you the most in, or like what kind of question fascinates you the most in AI research at this point in time.
Yeah, thank you, Manuel. It was a nice introduction. Looking forward. So I think the most interesting thing for me in AI at the moment is how do we make these general agents that can solve any task. And I think we have a lot of challenges to solve there still. In particular, causal inference and how do we generalize out of a distribution that we learned. So, for example, in reinforcement learning now, you have an agent that learns how to solve a particular task, but then it fails catastrophically in a different one, even if it has a lot of similarities. Um, so, yeah, in the near future, I hope that causal models, things that can make hierarchical action plans, for example, or quantify uncertainty, will be yeah, key tools to move forward there.
Yeah, maybe to narrow down on this a bit, I think like the key difference between AIs that we build currently, or what we call AI, and human agents is this kind of a more natural understanding of the world and kind of this transfer of skills between tasks. So why is causality in your mind so important in this context, or to according to a lot of people?
Um, well, like when you're an agent, you're making actions on the world, and things are going to change either in your favor or against. So if you don't understand or don't have a model of how how your actions are going to cause change, then yeah, you're you're gonna have to depend on luck, right? So currently, reinforcement learning uses Bellman's equation to over millions of trials. Let's say, having done things right and wrong, it will just know which actions are better and which ones are worse, but not the why. So causal inference is trying to understand or answer this why, so you don't have to try things a million times before you get it. You get this amortized action model.
Yeah, I think in our understanding, or this is constitutes more of an understanding of the situation, which relates to kind of not learning from repetition, but becoming a few shot or one shot learner by finding like more efficient, low dimensional representations of what's happening, basically.
Yeah, yeah. So in that sense, causal inference, I would say, is related to reasoning in our more natural language way of talking.
Yeah. I think there will be interesting things also talking that we're planning to talk about later about inductive biases and this kind of idea that language and consciousness are somewhat related in the way they help us formulate priors over or like learn out of distribution tasks, for example. Maybe now that you mentioned reinforcement learning in this setting, your master thesis focused on applying the free energy principle in a reinforcement learning context. So maybe we can just start there and go into the details of what you did there, and we also define the free energy principle and active inference and why it's so interesting and important right now in cognitive neuroscience and how it relates to AI applications.
Yeah. So active inference kind of promises to solve every problem that's intelligent agent related, um, but of course, it's not as popular as reinforcement learning, mostly because we don't have an efficient or scalable implementation. So when you want to publish something, you have to make it relatable or like interesting for readers to get into. So my idea was to try to use active inference to solve reinforcement learning problems and try to show that it can at least compete. And in my thesis, I worked on a small implementation for the mountain car problem. which is not generally it's not generally intelligent. But at least I showed some advantages of using this free energy objective instead of reward based optimization.
Yeah, maybe we can start at the beginning. Like, what is the free energy principle, and like, how does it translate to this reinforcement learning context?
Yeah. So the free energy principle is sort of the black magic behind active inference. It's actually a very general physics principle that applies to every self-organizing system. In this case, we can relate it to living things. So anything that lives in a medium that differentiates itself from the rest of the environment is a self-organizing system, right? If I'm a living thing and I go, I don't know, I go, let's say if I'm a fish, basically. Um, there is things that threaten my existence. For example, I cannot be out of the water, or there might be other fish that want to eat me, or I have to eat, otherwise I start degrading. And fish do all sorts of actions to secure their livelihood. So they are self-organizing in that sense. Um, what the free energy principle answers is what guides this self-organization. So these living organisms have um, have a model of their place in the environment, let's say, and their how they are organized internally. That's the genetics. Um, and this model, in an abstract way, we can represent it as a probability distribution of the states they should be occupying. So whenever they receive an observation, this generative model can tell them what's the probability that that observation matches the model that they are. So if I'm a fish and I observe that I'm out of the water, um, probably I will be very nervous or yeah, agitated. I have never been a fish, but I suppose that's how it works for them. But for a human, it's the same. Like if you're, for example, in a really hot desert, you will feel like you're in danger or stuff like this. So you have a generative model that tells you if your observations are something that means you're doing good to stay alive, or you should do something about them. Um, so to recap, this free energy principle just um, yeah summarizes everything about a self-organizing system into a single objective, that is this free energy. It's just a number that comes out of comparing your observations with your generative model.
Yeah, and then the idea of connecting this free energy to active inference or to living organism is that the free energy is minimized in a meaningful way during
Yeah.
cognition.
Yeah, so the free energy principle is the foundation. It doesn't tell you how the organism optimizes this free energy, and then on top of that we have active inference, which is just a corollary of the free energy principle that tells you how they do it. So living organisms optimize their free energy by both learning a better model and acting on the world. So if they see something that doesn't match what they predicted, they can learn about it, um, or they can also act on the world to observe what they wanted to observe. That's two ways you can optimize free energy, and basically what active inference focuses on.
Yeah. And the kind of interesting thing about these generative models is that, yeah, they correspond to a lot of, I think, at least concepts in cognitive neuroscience that have become more popular. This idea that the cognition is more like a controlled hallucination, and that, like, we, I think, historically underestimated, probably based on this empiricist heritage of thinking that we have a subject on the inside and an objective world on the outside, and the sensors give us kind of objective information about the state of the world. We are coming to the conclusion, or at least there's a lot of indication that the brain hallucinates or puts a lot of information into our perception of the world. I think this is where, like, part of this free energy principle or this idea of generative models of the world comes in.
Yeah, I agree. Like this framework just casts everything into inference. So instead of you are getting some inputs and converting them into some conclusion, doing inference means that you already have an idea of what you're going to observe and prediction, and you're trying to infer that prediction. So you're going to just um, you're going to identify things that are different and adjust your prediction. But there's always something or a state that you're expecting. That's the difference between inference and non-inference.
Yeah. In your paper, you also mentioned that priors in this framework and rewards are kind of related to each other.
Yeah, so a reward is an idea that comes from reinforcement learning, and it's a very intuitive one. So you want your agent to do things that are rewarding. So, for example, if you want your agent to reach a state, you're gonna give rewards the closer it gets, and give negative rewards the farther it gets away. And it's very intuitive. You can easily set that up, and the agent will try it many times and eventually learn some utility function of how useful is a state with respect to this reward. But it's kind of blind to what it's actually doing, right? In active inference, you don't have rewards directly. You have states that you want to reach. So instead of just telling the agent like hot or cold with respect to some objective, in active inference, you just give the objective, and the agent will tell by itself if its predictions or its inferences are close to what the preference is or this high level objective. And on top of that, Active Inference also optimizes for internal rewards. So not a reward that comes from the environment of like you're reaching your goal, but also internally, agents want to minimize the surprise of their model. So if you don't have a good model of the world, whatever you observe is whatever prediction you make is gonna be wrong. So you're also interested to learn about the world, and that gets mixed in the objective function of Active Inference. And yeah, one of the interesting points of this is that it implicitly solves the exploration exploitation problem because it's both trying to reach external objectives while also optimizing internal ones.
Yeah. I think one of the critiques that people that encounter this principle for the first time often have, and I know that you had it and, and wrote to Carl Friston about it, is this idea that if we just want to minimize surprise, why don't we stay in a dark room without any sensory inputs? So what drives us to push exploration?
Well, yeah, you don't. Of course, you want to see your predictions being fulfilled, but the question is, what kind of predictions do I make as a human? Um, what we call these models that we have biased generative models because we just don't predict we just don't predict the whole world. We predict very particular things. So I want to predict things that make me survive, for example. So if I stay in a dark room all day long, after a few days I will start to degrade.
Hmm.
um, Also, these agents are usually limited in computational power. So if I'm, for example, if I'm an ant, for example, I don't have like a full 360 view of my environment, probably not even an image of it, or like a few signals. So yeah, my sensor input is very limited. I'm gonna have to optimize what kind of predictions I make that are useful for me, rather than trying to predict everything. My brain is also smaller. I don't want to waste energy. Um, Also, other issues is that the environment is some things are non-predictable, so we need to focus on the ones that are predictable. And so evolution just gave us this biased model.
Yeah, and there's a lot of prior structure already inbuilt by evolution, like by the way
Mhm.
we set up and even by the way our sensory systems are set up. Like
Yeah, yeah.
even vision is inherently biased because we can only perceive a certain wavelength spectrum of like the objective underlying reality, and then we have probably, I don't know if that's, we perceive red colors probably more vividly than because it triggers certain reaction like.
Yeah. Yeah, I agree. We have both like physiological priors, like you're saying. I think there's also really interesting behavioral priors that come and that are studied in affective neuroscience. Now, for example, display behavior of mammals is said to be one of the main reasons we form like societal organizations, and that comes just because we are motivated to engage in play and interactions um, with other similars to us. That doesn't happen with other animals.
Even though some like I think other mammals also play. Rats also have this like brain area that is specifically responsible for play between rats, and they even feature like similar behaviors.
Yeah, I think it's present in all the mammals. So they have this 60-40 rule, I think, where you want to win 60% of the time while the other one loses 40%. And if you don't take turns, then the other one will get demotivated because he's losing too much. But then you will get sad because you're not playing anymore.
Yeah.
And then eventually this creates these societal rules of like, okay, like sometimes one is the boss, but we need to also listen to the others. And it just creates something that
Yeah.
works
Yeah, I
somehow.
recently talked with friends about this in the context of like online chess addiction, because like the kind of the elo system is structured in a way that you always play against people so that the expected ratio is 50-50, which makes it the most fair, but it's also maximizes dopamine because it maximizes the entropy of the result you're going to get. And I think it's kind of tied to this intrinsic, maybe even addictiveness of gambling, and like I guess online chess, or playing games against people that are your strength level approximately, kind of has this addictive quality precisely because the uncertainty over the result is maximal if it's this 50-50 or 60-40
Yeah.
rule.
Yeah, it's this thing. Like I'm gonna get demotivated if I lose more than 40% of the times, but I'm also gonna get bored if I win more than 60% of the
Yeah.
times. Then it creates this
Yeah.
balance.
Yeah. So talking about trials in general, I think this is a concept that's also difficult to grasp because according to Friston, this free energy principle applies to like very different scales of organisms. You can think of it on the cellular level, but you can think of it on the level of the entire human brain, for example. So like,
Mhm.
how do you think of these kind of prior models or inbuilt models that then are able to make predictions about the world?
Yeah, I have a small example that maybe can make it very clear what's the difference between RL and active inference. So one of the difference between the way we use models in both is that so in dynamical model we have two types of modeling. In dynamical modeling we have two types of models. We have forward models. So given a set of causes, you can generate what you expect to see in the world. So you give motor actions, and the model will tell you where your actuator will be, let's say. And then we also have inverse models, inverse dynamical models, where you tell where you want how you want the world to look, or where you want your actuator to be, and it will tell you what causes are there, or how you have to actuate, what motor commands you have to give. So the big difference between active inference and reinforcement learning is that in active inference, almost all the models are forward models. We make predictions. Whereas in reinforcement learning, the models are inverse models. So we get observations and we produce a candidate action directly. And so to compare, let's say a self-organizing system could also be an organization, like a corporate. Like, let's say, for example, I'm working in Google, so let's take this example. If I'm the CEO of Google, I'm gonna I'm gonna have a prediction or a preference of where I want things to be in a month or in a week, and I'm gonna communicate that to the people below me. Probably it's 10, 15 people, and the people below me will take my predictions as preferences that come from above and have to be fulfilled. And they themselves have their own model of how things should be in that time frame with respect to the prediction that came from above, or even in shorter timescales. So if the boss says in 1 week we need to have an approval from this client, then as the person below, I know, okay, then in 1 day I should get reply from this person below that this is fine, or from legal department or whatever. And then each of these people will have people below them that will do basically the same. So each step in this hierarchy has a forward model that is biased on whatever order came from above. In active inference, we call it a prior or a preference. So eventually, this reaches all the way down, basically where I am. So for engineers, where I get a preference such as yeah, we need this function in the product, and then I'm gonna be the one typing it down and actually performing the action of having that in the product, which will cause eventually that the client will be happy, and that will propagate up all the way to the boss, having the client approving some purchase or whatever. So as you saw in all this process, almost everything was forward models until the last moment where things became an inverse model, no? Where I was typing things and actually performing an action. Um, Instead, in this example, what would be a reinforcement learning agent? So it would be me entering a job where I have no idea what I'm gonna do. I'm just in a room with a computer and I start typing. And after 1 month, I get my salary. Then I keep doing my stuff, and the month after, my salary gets higher. So something went right. Then I keep typing. Then the month after, my salary got lower. So something went wrong. Then I'm gonna keep doing that for, let's say, 10,000 months, 20,000 months, and eventually I'm gonna start to understand what kind of things make my salary go up. And I'm pretty sure that if I kept doing this for a long time, I could even start to understand what the product is about.
Yeah.
So that's basically what reinforcement learning is doing. Um, so the organization can still be the same, right? There could be bosses and so on top of me, but it's not part of the model. I'm not receiving their preferences. I'm just sending my output out. They will evaluate if it's good, and they will decide my pay. So that's the reinforcement signal. Um, and essentially, in reinforcement learning, that's what we do. We design an environment to test our agent, and next to it, we also designed, the engineer is designing reward signal for it. In Active Inference, the reward signal is computed internally. I receive a preference, I know my model, I know what I want to infer, and then um, I expect things to be as I predicted. If they are not, I will be surprised that that's my signal that I should do things different. But that's computed internally from the things I observe. I don't need a reinforcement signal. Um, yeah, I think that's. I hope that's a good comparison.
Yeah.
Um,
Definitely illustrates why the free energy principle would make more sense for like real cognitive agents, because I mean the reinforcement learning cases seems really impractical from that perspective of in real life you don't have enough time to explore sufficiently, and the reward landscape will constantly change in time.
I don't think they are completely exclusive though. Like, even though beliefs or preferences or priors are way more expressive than rewards, sometimes you just need rewards because you don't know what you want. For example, um, if I'm a toddler and I don't know that electric outlets can hurt me, I don't have a model of that, so I cannot decide whether it's good or bad. Eventually, I'm going to touch it because I'm curious, and Active Inference tells me that I should try to reduce my uncertainty, so I will do it. And I will get electrocuted, and that will be a very strong signal, no? Like, pain is more of a reward signal rather than a prior. That just tells our model, like, yo, you need to learn this thing, don't touch them, they do this, and that will become a prior eventually, but at first it was a reward signal. So the concept, it came from an intuition at the beginning when they invented reinforcement learning, and I think that the intuition is still very right. And it will for sure make part of active inference agents as well.
Yeah, I think there's also, like, at least my supervisor likes to talk about this as well, that like some features of reinforcement learning, or like the way rats, for example, learn, and the way we have this kind of rule learning, which is discontinuous but kind of tries out a certain hypothesis, and then you have this sudden bifurcation which implements a rule learning switch, and then suddenly the red instantiates a completely different new rule that's than the correct one. Is something that's hard to replicate with reinforcement learning, because you usually have like continuous deformations of the reward signal, for example, or continuous learning of the process. And then it probably makes more sense to approach these kind of ideas also from this free energy perspective, that we actually have a prior over, we have different rules and hypotheses that we try out, and that we assign different probabilities to, and then
Yeah, so exactly what you're saying. When I receive good signal out of a state that I reached, it will become highly probable in my biased model, which means I will want to infer that kind of state in the future.
Yeah. I think one other like really interesting aspect of the free energy principle is this idea of that these generative models are also statistical and that they have some kind of explicit representation of uncertainty, which builds on this assumption that the world is always uncertain and that there's like one of the central elements of cognition is to basically construct an internal landscape of the uncertainty over different data modalities and different like physical spaces and to kind of assess that constantly while we are walking around in the world.
Yeah, so yeah, basically the objective of intelligence in this sense is to automate things out, right? So if I repeat a thing and it gives me a reward, then it will become very probable that I predicted that I'm doing that thing. And in active inference, a prediction becomes also an action, right? Because you're trying to fulfill that prediction. So eventually it leads to habituation. And when you are used to something, you're not thinking about it. How I prepare a tea, for example, I don't even think about it. I can be talking to you. I've done it so many times. Um, the way I get to work, the same, not even thinking where I'm going. Um, so yeah, I mean, these predictions are intrinsically connected to the uncertainty that you have in your mind. The more certain you are, the more automated, the less you think about it.
Yeah. One idea I found really cool in Bengio's paper on these inductive biases is this hierarchy of timescales and kind of I think there are several hierarchical models that are connected in deep ways. These hierarchies of uncertainties, we basically have elements of the world that are stable across even generations, and then you have cultural evolution, for example, taking place, and like even on a larger scale, on an evolutionary time scale, the fact that all of us breathe air is related to the fact that there's been oxygen in the atmosphere for millions of years. So we are very certain of that, and we don't evolve any lungs that have the ability to breathe anything else. Then you have the cultural evolution timescale, which creates structures that are also longer lasting than each individual human being because there's not a lot of uncertainty in that aspect of the environment over with needing that kind of variation. But then like the lowest level of the hierarchy and maybe also connecting that to your Google hierarchy is like on the lowest level you have uncertainty over how best to implement the code and then you have bugs and something like that, but the prediction errors you face are also taking place on small time scales, but the CEO has to do strategic decisions on the scale of years maybe.
Yeah, yeah, of course. I mean, um, yeah, for the task that I'm doing, for example, let's say this, it's related to an idea of the CEO that we should open this new division about AI to these kind of clients. And this means something needs to be developed. His vision is 1 year forward, and all the way down to where I am, things are happening every second, right? I'm typing things on the computer while I'm trying to fulfill his prediction that's 1 year forward. The people below him have a slightly smaller timescale, so it's all the way down to me. So yeah, definitely what you're saying gets visualized in this way. But also above the CEO, what is above him would be the top, the big question. No? What's the top level prior? And it goes also into evolution, right? Because a company has its own DNA, and a big chunk of that DNA is, let's say, um, leadership, general knowledge, or how organizations run. This has been optimized over hundreds of years, and that's also how Google got there. It doesn't do things fundamentally different from other organizations. Of course, it has many differences, but fundamentally, I don't think something like the way we work now would have appeared 100 years back, just because they didn't. They needed a lot more iterations, right, to get.
Yeah, I also like the idea of basically that in cognition we decompose the world model into these static parts that are things that have worked and that we can more in like this symbolic AI approach actually commit to memory and instantiate as rules that are like immutable. And then we move to these latent variable or like generative models that are responsible for the parts that feature a lot of uncertainty and like flexible out of distribution learning and kind of adjustments.
Yeah. So um, about this latent representation models, when I, when an agent is immersed in an environment, it receives a lot of input, right? Like I have a lot of sensor inputs in my body, all over my skin, all over my retina, and so on. And so I cannot process all this information. So I'm gonna have to select something. And in information theory, we have information has a different definition that one we normally use in language. So in information theory, information means it's the part of an observation that you cannot predict. So the novelty that comes from it. Um, and normally these latent models, what they want to do is to extract from the input information that is useful for them. So sure, I could predict how it feels, the contact of my skin with everything I touch. It's just not useful for me. So I'm gonna have this model that will completely ignore these inputs. I'm gonna focus on a generative model of what I care now, which is talking to you and seeing your reaction if you like what I'm saying or not. And that's where I'm gonna focus my predictions. So if I'm predicting that you're happy, or I'm preferring that, and I see you not so happy, um, then the information will be very high because it doesn't fulfill my prediction, and then I'm gonna have to do something about it. So we have these latent models that focus on the right inputs to make the right decisions, and I think that's a really fast moving field in machine learning. It's called representation learning. So how do we extract from input data what's relevant to some task or reconstruction? um,
Yeah, that's again, a very interesting topic in its own right, and it kind of decomposes into these self-supervised approaches and semi-supervised and fully supervised approaches, and then you have like different ideas of how to get to these representations. Where we can also talk about this.
Yeah, so for example, I think it's super common these days to use this for images. For example, if you want to tell if there's a cat or a dog in an image, and your images have a million pixels, the information you actually want to get has only two dimensions, right? How much of a cat is there and how much of a dog is there. And there's even a relationship. You should not see a cat and a dog at the same time. So the dimensionality of the model that you want is really, really more, really low, whereas the dimensionality of your input is huge. It's like millions of pixels. So you want to have these models that are going to learn a way to represent these 1 million pixels in a few dimensions, so that it is much easier to tell if there's a cat or a dog in there. And then we normally use autoencoder type of architectures that um, process this input in stages and try to compress it in smaller and smaller representations. And then the objective is to then decompress it and get back the same input.
Yeah, maybe. Yeah, talking about these, I think in these labeled examples, then you try to get from the image to the label dog, which is essentially like a strong dimensionality reduction approach. But in the like unsupervised setting, you're trying to find more general meaningful representations of how you can compress images, for example, or how can you find an encoding for images that's really not task dependent, but will help you down the road if you want to, like independent of whether you want to classify dogs from cats or horses from donkeys or something like that, because then it extracts kind of like a more meaningful, like abstract structure. And I think at least in the visual cortex, you can also claim that something like that happens, that
Mm.
we first start with these extraction of these shapes and like more abstract classification. This could be a mammal, for example, is like a more abstract class than dog, cat, or horse.
Yeah, yeah, you're right. So my example was, as you're saying, a classification example, right? When you know in your data that you have cats or dogs, the question is what if you don't know? What should you represent in these low dimensions? Um, and the answer comes from from the structure of your data. So if your data is pure noise, then a pixel doesn't you cannot predict a pixel from its neighbors, right? It can be any color. um, but if you feed images of cats to a model, eventually it will know that if it saw something that looks like an eye here, probably there's another eye at some specified distance. And then every pixel can be predicted conditional on the rest of the pixels of the image, and then you can encode these correlations into increasingly more compressed spaces. We call it sufficient statistics. So if your data is about cats, there is a generator function that, if it has high probability of cats, it should output images that look like a cat. um, and if a cat input comes in, then it should also map into this area of this probability function where it's high probable that there is a cat, even though you don't know there is a cat. But it's just that it just falls in those kind of images that look similar. And you can do that not with just cats, but like any kind of image of the real world. The world has structure, so if you have a big enough model, it will learn that structure into these latent spaces. If you give it enough size, of course. If you give only a one-dimensional space, it will not learn um, everything about the world. Just the most frequent occurrences, or like
Yeah, one of the interesting applications in this context is also transfer learning when you pre-train very large models. And I think Google routinely does that with large scale language models, but you can also do it with image classification, that you basically use a pre-trained model on a lot of different images, and then you just need pretty low dimensional model to do a classification task with it, because like the feature extraction that is useful for your classification tasks is independent of the details of what you're trying to classify, but really works on more general structures that you extract from the data, like latent representations.
Yeah, this is a really trending area in machine learning, just a few years old. And it came from the discovery that if you have really, really huge models and really, really big data sets that are very diversified, these generative models are going to learn um, latent representations of these data sets that capture very efficiently um, the kind of objects or things that happen in there, and even their relationships. So if you have such a model, then you can use it later on to fine tune on your particular task. um, and it learns way faster because it already has knowledge in there. So, for example, in my classifier of cats and dogs, before it could have taken, let's say, 1 day to train on an old GPU. But now, because we have these huge models that contain already knowledge of how things look, probably they already know how a cat or a dog looks and 10,000 other objects. Um, I can just put my classifier on top of that and train it in a few minutes, sometimes even less, because these models are few shot learners, right? They just need to increase the probability outputs for these categories because you want it to get more accurate, but they already do it normally if the object is very frequent.
Yeah, I think that's one of the fascinating aspects that also will bring us closer to like what we consider to be more general intelligence, because few shot learning is like kind of a at least a way towards out of distribution learning, because it's connected to what we talked about already, this idea of understanding being there, there's like a more generalized latent representation of certain things that's not overfitted on a specific task, for example. With
Mhm.
GPT-3 you also have this few shot learning.
Yeah, you have this I think language is a very interesting case because there is a lot of structure and knowledge in big corpuses of text. So if you train on Wikipedia text, then you do very good in answering all sorts of questions that don't appear in Wikipedia, or some downstream tasks that you didn't train on. Like, for example, you can ask things about, I don't know, you can ask personal advice to one of these bots, and somehow it knows how to
Yeah.
chat. even though it's just so Wikipedia articles. Um, or maybe you just need to fine tune it a little bit to get it to chat properly with with a convincing way. Um, because it just knows how words are put together, what they mean in contexts, and so on. Um, and it's really useful because sometimes you just don't have enough data, right? If you want to train a chatbot for your particular application, maybe you don't even have data yet because you're just starting. You have a small data set of like a few hundred or thousand conversations. um, that is not enough for a language model. A language model requires millions of examples, but you can pre-train it on Wikipedia data, and somehow it works because language is kind of the
Yeah,
same.
I think these are things that are really surprising, intuitively speaking, surprising for a lot of people, but also extremely useful because I mean the language models have reached a size with 175 billion parameters that it's just so expensive to train them. You need like 10 billion or like $10 million in electricity bills, I think, for the GPT-3 or something.
Yeah, yeah,
So only like no small research institute can do it and no small company can do it or a private person. But if you have that kind of hierarchy between the pre-trained models and the fine-tuning for specific tasks needing much less energy, then it's also quite useful for a lot of real-world applications if these pre-trained models are out there. And a couple of companies, I think Google also put it out as open source. I'm not sure which one it was, but
yeah. Normally, these checkpoints are open source if they are safe to share. Because if you use um, some private data, then you
yeah,
can't, right? If because these language models also encode knowledge implicitly. So if I ask for the age of some US president, it will know the answer because it not only learned about language, it's also learned relationships between words, and it will learn that the highest probable word following the age of Obama is, it will be that particular number. So um, yeah, you cannot open source a checkpoint that comes from data that's sensitive or from a client or whatever. But normally they release these ones from Wikipedia and open data, and they are
yeah,
extremely useful.
yeah. I heard that in the context of these AIs that help you code, which basically autocomplete certain functions, that this there was a bit of controversy around this model that GitHub now offers for developers because this was trained on like all GitHub repositories, and some of them are open source repositories, for example, or some of them I'm not sure if they are all public. But then you train
Yeah.
on data that's open source, but you make a commercial model out of it. So it can be a bit tricky. Wikipedia also is like crowdsourced. So if you train on that, these models written by people, these texts written by
Mm.
people as open source, and then you sell a model out of it, it becomes quite tricky. What, like in the day and age of like intellectual property, how to define that properly.
Yeah, yeah. I think it's a very hot legal topic at the moment, how to apply copyrights to these models.
Yeah. Yeah. Also with generated images, like with DALL-E, for example, I just
Mhm.
generated a couple of images today, and then if it looks really cool, if you use it as a logo of your company or something like that. But it was trained
Yeah.
on images that other people actually created.
Yeah, it's a very strange discovery, that you can encode information not like explicitly in a file, but as part of a process. So, like in DALL-E, for example, I can generate images that look very similar to some particular
Yeah,
artists, but these are not stored anywhere. They are part of a denoising process. And for sure, copyright laws didn't think about
yeah,
it before.
yeah. It's good. It's just you put the information out there if you paint something in your style, but that wasn't a problem. I mean, people imitated other artists before, and there was a lot of controversy about did that person actually paint this painting and stuff like that.
Yeah, yeah. I guess they should apply kind of the same
Yeah,
process.
yeah, but it's interesting because I mean, in the brain, we kind of are confronted with that fact every day that we have like abstract symbolic representation in language of what we know, but most of our knowledge is encoded like in the process of our actively cognizing. Like we can recognize a lot more faces than we can actually remember directly. So it's like always a lot of the
Mhm.
knowledge that is stored in our brain is.
Yeah, I agree. I think our our conscious perception is kind of like comparing it to this example of a corporation. Let's say our conscious state would be the CEO, and possibly the things that he knows about of the ranks near him, but for sure he's not aware of what I'm doing in my daily life or ever. And so that's akin to what happens in our brain. Like we're conscious of the very high level thought processes, but they get decomposed into lower and lower states that we just became uh, less aware
Yeah,
of.
yeah. Bengio proposes that the conscious processing and language are very closely related, also connecting it to this global workspace hypothesis. So the idea that we have a lot of different sensor modalities that we are like in parallel making predictions about potentially depends on how you want to think about it, but in this active in
Mhm.
this free energy or like active inference framework, we have a lot of sensor modalities, and then as at one point in time we encounter like some kind of uncertainty in one sensor modality, and then that information in that sensor modality needs to be made available to like the entire brain and maybe like the larger world model, and then we activate that and put that information into the global workspace. And this is like a workspace that's connected to language because it's we can think about it consciously and put it into concepts and ideas.
Yeah, yeah, like we have these generative models organized kind of in a hierarchy, right? Where it starts becoming more abstract as you go up, both spatially, and temporally. Like the content of the information becomes more abstract, and also the timescales in which we make predictions become more enlarged. Um, so, for example, if I have a subsystem that focuses on making predictions on visual input, eventually it gets into a really high level state in which my predictions are very um, factorized, or like I either see a screen or I see a background, but not the object inside of them. I abstracted that away. Um, or yeah, my predictions also become a longer time scale, and then eventually that merges into a higher level system where another input stream comes in, let's say auditory, where predictions are also happening. So things have to be very abstract there because you're mixing two sensory streams, and you need to only focus on the information that is um, shared between them. um, So eventually, as you go up and up and up, you end up in these spaces where things are very sparse, um, and but still they have to be connected somehow in a way that's useful, and that's what Joshua Bengio calls the consciousness prior, and sparse factor graphs, and he puts language as a candidate where these tokens are these factors, or yeah.
Yeah, and he connects it to the idea that also in language you have relating that to this causal inference idea that in language we very frequently represent causal agents that can have some kind of strong impact on shifting distributions, for example, that we observe in reality. Because this is in principle what primarily is done by agents or by or probably most frequently done by them because they are not part of the or they are harder to expect. It's harder to expect what they're going to do. There's more uncertainty inherent in their actions.
Yeah, it's also very interesting the limitation that language is strictly serialized. So you cannot have uh, multiple meanings or paths of thought in when you're thinking in language, right? Things are happening in a single string. So in there are many tasks that you cannot do at the same time, such as like listening to someone and at the same time writing down about a completely different topic, because at the very high level things uh, are yeah, our thought happens in language, um, and somehow is single threaded. mm, I don't know exactly why there would be such a limitation, but I guess it's a useful way to, yeah, to model these out of distribution shifts between
I
things.
mean, I don't think thinking per se is, or even conscious thinking is only done via language. I think that's only a byproduct. And I think a lot of people think very differently. Like, I think every person has their own like
Mhm.
approach, or yeah, some people think more visually, some people think more in terms of language. And I think it's probably, or you might argue that it's also a byproduct of social evolution, that we are kind of forced to explain ourselves constantly, even if it's not really very
Yeah.
coherent or doesn't really correspond to what we're actually thinking. Or
I think on a high level, we all think in language, just that it doesn't really mean English per se, but it's a tokenized
yeah,
version of whatever happens in our head. So, like, if I'm an artist, probably I'm not thinking as an English novel in my head, writing paragraphs. But I'm probably thinking about discrete objects or relationships between them in a very sparse way. So. Um, I cannot put you a concrete example, but let's say if I'm Miro or Dali or people that did really abstract stuff, probably they saw um, very structured or concrete relationships between what they were doing, at least in their head, and that's why they can put together such coherent artworks or storylines, even though they look
yeah,
abstract to us.
especially if it's in a multimodal context. Like if you have a Wagner opera, for example, you have text and visuals and music.
I think it happens with every field. When you get really good at it, you start to think in terms of that kind of thing. Like if you're a
Mm.
musician or something, you start to have really particular structured ways of thinking about it. Whereas I'm not a musician, so when I hear music, I don't know what to think. It just sounds good. Probably they can see things like, ah, this is do, or this is me, or this is this accord, or this kind of rhythm. I cannot put names to it, or I don't detect that they are similar to
Yeah,
previous ones, but they do
yeah, yeah,
for sure. So those are these tokens that they convert into their own personal language.
yeah. Yeah, in music, you also have this. You develop this kind of vocabulary, and depending on your model of the music that you build, you build a certain expectation over what music is going to sound like, and that
Hmm.
model, going back to the free energy principle, basically determines the surprise you experience while you're listening to music and the information content of the music. And then that's why jazz sounds like noise to a lot of people. If you're not a jazz musician, it's actually noise because you
Yeah.
don't have a very good model over what the music is going to do, and then you just don't know what it's doing. But if you are used to listening
Hmm.
to jazz, you hear certain structures, and then you basically reduce the amount of uncertainty you experience while listening to jazz, and then
Yeah.
it like finds the right place at the edge of like chaos and order. Yeah.
Yeah, and probably when I start to have a lot of experience and I can have like precise thoughts about it, then it becomes easy to invent a language or acquire one. Like all of these fields for sure have their own vocabulary and ways to describe things. And that's something that happens naturally for humans. We invent languages whenever something becomes useful to communicate.
Yeah, and as societies, we invent concepts that make it useful to think about the world. I think these concepts also
Mm.
really depend on the state of the world. I think many of the concepts we have right now, people just didn't have 500 years ago.
Yeah. Yeah, so that's why I think language is a very good candidate as a top level cognitive process. And in fact, is one of the definitions that machine learners are starting to pick as consciousness is whatever cognitive process you can serialize into natural language is conscious. I think it's a very broad definition, but it's very useful for reverse engineering. So, for example, in neuroscience, I think one of the most trending definitions of consciousness is that it's the joint perception of external and internal stimuli. Um, so in your head, you have, let's say, an older brain, this reptilian brain that's very simplified, but given some input, it can tell you um, some very primitive actions, and those actions get feedback into our neocortex. So neocortex is basically processing inputs from outside, creating a very structured model of it, and sending a summary to this reptilian brain, which is going to tell the neocortex, oh no, this is scary, get out of it. And the neocortex is going to have to figure out what to do in each situation. But this conversation that happens between the two is the candidate that in neuroscience currently they are calling consciousness. This kind of perceiving that this thing that I'm seeing outside feels like this other one I saw before. That's being conscious about what you're perceiving. Um, and yeah, I think eventually this kind of process leads to what we just talked, these high level concepts or tokenized things that humans converted into language, because we have part of the brain that evolved to be really good at it. And machine learning is taking that outcome and starting to reverse engineer from that. So I think it's
Yeah, I think there's like two different, very interesting things. I'm not sure which one to start with. Like probably, yeah, I think this idea of the language before language, like this mentalese that has been around also in linguistics. And I think there are some opponents to that idea, but I think you can like the as a step before language that probably like human like civilizations had before they developed like really more complex languages and complex vocabularies was this like multimodal latent representation of our different modalities in the world that you could use then in this consciousness prior kind of way to like in this global workspace or however you want to approach it, that you have these low dimensional sparse latent representations of what you observe in the world, and that can then be used to like make higher level decisions and actions and plan actions, for example, in this space.
yeah. Yeah, I think language and conscious perception or high level thought co-evolve with each other. It's not that language comes after, but it also it's predecessor for many of my thoughts that will come after, right? So if I don't know anything about architecture, I'm gonna run into a city and will just look things will look nice or big or very simple
Mm.
interpretation of things. But for sure, if I take a course on architecture and I start to learn the names of things of like, oh, this is this kind of column, it comes from this epoch, it has this name, then I'm going to focus on a lot of different details. I'm going to have more precise ideas, or I will be more creative. So language for sure enables that. Um, it does, of course, someone before had to come up with these words and invent the language, but then it creates this loop, right? I think there's a very interesting thing in history that whenever a new kind of language comes in to talk about something, all of a sudden you have multiple simultaneous discoveries of something new that is enabled by that set of new words that allow you to have really precise ideas about something and construct newer ideas. So yeah, it's a co-evolved system.
Yeah, I think probably cognition also works pretty well without language, and we don't per se need language, but like from a social evolution perspective, it's extremely useful because it kind of couples human beings to each other and gives us the ability to develop shared concepts which really help understand the world and like better manipulate the world, and it also helps us communicate
Mm.
in a general sense. I think I would argue, or probably it's like more speculation, that we don't need language to think by ourselves, but it's just useful as a social product.
I'm more of the opposite idea. I think without language, our thoughts would be very diffuse. Like our pets, for example, don't have language, and if you observe them, their behavior or what they seem to do looks very fuzzy. Like sometimes they're running in some direction, it looks like they didn't decide why, or I don't know. They just don't look as decided or intelligent as we do. For sure, they know how to survive and be happy and so on, because they have this internal prior that gives them a direction of how to do things, but they are not really reasoning them. Um,
Yeah.
of course, I think you could be a fully functional human being in a jungle without language, and you might survive. Um, but you might not invent, for example, fire or tools that took us millions of years until we could communicate and think about that, right? Because we
Yeah.
had language.
Yeah, that's an interesting question. Like kind of a chicken and egg problem. If language was necessary to push us to become more intelligent, or if we became more intelligent and thus acquired language, which in turn pushed us towards. Oh,
I think it's just very useful to make ideas precise and
yeah,
composable, and yeah.
but that's like from this mentalist perspective. I don't know if we can develop these latent representations without verbalizing them. I think we do that constantly with a lot of sensory modalities. Like toddlers also acquire like some low-level concepts before they acquire language.
But I think it's the same we talked about before. We acquire these tokenized mental states, right? Things that seem to occur often or that are useful to do, and we just turn them into an object in our mind or
Yeah,
a concept um, that later we put a sound to it to communicate. That's the externalized version of language. Now, but internally, we construct languages
yeah,
naturally.
yeah. I think then we basically mean the same thing. I think this internalized language is extremely useful, but the externalized language is more a byproduct of social evolution. Yeah, but it's interesting to like from this perspective of language models to to ask ourselves how far we can get by like backwards engineering that externalized language that we have on Wikipedia and other corpora, like how much information about the world is actually already encoded in these language models or contained.
Well, you have this very recent example of, I think it's made by a team in Google Robotics. It's called Seikan, this model where um, the robot basically has a language model where you can tell him, like, can you bring me a Coke and something sweet? And it will it will use the language model to create a set of steps. So that will become uh, go pick a Coke, go pick an energy bar, they are in the fridge, go to the fridge, and the language model can understand at least the top level steps to achieve that objective. um, then of course in language we don't have a lot of causal knowledge encoded there. For example, um, I don't think I can describe you how it feels to ride a bike. um, for sure I can tell you, like, I'm sitting there and pedaling. It's a bit dangerous when I'm slow because you might fall, but the actual feeling of it and how the actions are performed precisely, it's not something that you encode in language. It's more of a piece of causality and dynamical models, which language is not really made for. um, but that only happens at a lower level, right? In a high level, when I'm riding a bike, I'm not thinking about those things. I'm just feeling them, but I'm thinking about going somewhere, moving forward. So these Seikan models do basically the same. On a high level, they tell the robot um, what they have to get and where, and bring it where. um, the actual motor commands come from other models, not the language model, that are connected downstream.
And are they implemented top down, like, or do you have like a lookup table for specific actions that the robot can do?
I don't really know about their implementation, but I don't think it's end to end. Like they might have already like a command that you say, grab object on the table, and they already have an algorithm to do that. But it's not trained end to end. Of course, that's the end objective of it. But um, if that was easy to solve, we would probably not have
Yeah,
this talk.
yeah. It seems like not the best way to approach robotics. I would argue. I would get like also with self-driving cars, you probably don't solve that starting with a language model, for example. I think there needs to be like
Mm.
different aspects of building generally intelligent agents that are really focused on this acting in the world with this embodiment.
But I think that what makes this option extremely interesting is that when you have these hierarchies that we talked about before, you need the top level to give the command, right, to the ones below. But if the top level is in a really abstract space, um, as an operator of that robot, I'm not going to know what high level command I have to give in order to get the action that I want. But if that high level can be serialized into text, um, or I can speak to it and it can be converted in a high level prior for that robot, that's extremely useful because all of a sudden I can give really high level commands as they do in this Seikan example, where you're like, can you bring me a Coke and something sweet? and it does a lot of really complex stuff out of this command. I think that's super
Yeah,
powerful.
that's definitely a good point. This translation process, going back to your Google analogy of what the CEO says to the software engineers, actually trying to work with the implementation, and you need to translate that high level statement that's encoded in language into more concrete steps down the road that you can actually implement into actions or price.
Mm.
Yeah, that's true.
Yeah.
Maybe going back to like language models a bit more generally to understand a little bit what they work with these days and what kind of made like the largest shift in the success of language models in the last couple of years, maybe transformer architectures.
So I guess the first question is, what is a
Yeah,
language
we
model?
can start there.
Um, because we're talking about it, we can suppose it's something that knows about language, but in what way, right? Because we are using it in a machine. Um, so a language model is a model that can tell you the probability that a word has to appear in a certain position in a text. So if you run it for all the words in a paragraph, it will tell you how probable is that paragraph in that language. So if I write a paragraph with random words, they will get a very low probability of being next to each other. So that paragraph is not language. So the language model, it will just give me a thumbs down or a very low score. If I instead assemble a very good English paragraph and I feed it into an English language model, it will give me a very high probability for every word being there. Um, and you can use this for a lot of things to make predictions about text. So, can you finish this sentence? Or in the case of code completion, like we were talking about before, I can start feeding the first few um, words of my function, and then it will tell me all the ones that are most probably that come after, and somehow that's actually really accurate, and it can produce even well-formed functions just by calculating probabilities or things being next to each other. And that's actually how we train language models. Like, we take paragraphs and we mask out words and we make it predict the words that were maxed out. So if you do that for millions and millions of examples or all of Wikipedia's corpus, it will eventually learn um, the contextualized definition of those words. So before language models, we had these word-to-vec models, where you can feed a word and it comes out with a vector of numbers, and that vector somehow reflects the meaning of that word without a context. So I could do operations like, I have the word king, I subtract man, and I add woman, and somehow the embedding that comes out is very close to the embedding of the word queen. That sounded like magic at the time. But that doesn't work so well for words that are very dependent on context. So, like things like pronouns, um, adverbs, verbs, um, they really depend on where they are used, right? So, this work to work approach is not so powerful anymore. Um, Instead, with these language models, you get an embedding for every word that is conditioned on the words that are next to it, both behind and ahead of it. Um, so yeah, you can differentiate. For example, if I'm talking about my friend and our bank accounts, I can say, yeah, my bank is AVN and his bank is Rabobank, and then later on in the sentence, like, by the way, I'm going to his bank. The language model is gonna know that that bank is Rabobank and not AVN, because of context.
Yeah, and that context question basically also relates to like the size of your model. And with previous language models based on RNNs, you get these tricky like memory problems that are connected to exploding vanishing
Yeah.
gradients. So it's harder to connect words that are spread out like a large margin if you don't have networks that explicitly incorporate memory, for example.
Yeah. So the big limitation of language models at the moment is context, the context size. So the memory that they use increases quadratically. or even exponentially. I don't remember. Um, but there is a hard limitation by software that you cannot have more than, let's say, 500 words in the context, because otherwise you're using too much energy and memory. Um, and yeah, and there is a lot of work being done to increase this limit, and tricks to avoid this quadratic growth in memory. But basically, what you can achieve is, for example, when you read a novel and you like progress through it, the name of the character acquires more and more meaning, right? Because every time you read that character, you know more things about it and more things that it has done, or you can even predict what's gonna do next. So you get to know him better, and all those pages that came before are context for you to understand this character or the objects around it if they are relevant to the storyline, right? A language model is only going to know that character out of the stuff that it read in the page before and the page after. So it might not be enough to predict if it's the name that comes next or is the name of another character. If you increase the capacity, then it would be extremely precise in its understanding of the story. It could even create, the second book or the eighth book of Harry Potter out of reading the previous ones, and it would be extremely convincing, probably super interesting as well. Um, yeah, then also in applications like code completion, if you can have a language model that can have as context your entire code base, then most likely it will produce really accurate functions. It could even like um, yeah, be so accurate that you can on a high level describe, yeah, I want an app that does this and that, and it could generate the app because it just knows all the code base extremely well. That's the real power when you increase
Yeah.
context.
I think one of the powerful things about transformers are that they don't have a lot of inductive biases about, even you don't need to have any inbuilt idea of how language works. You just can just use self-attention and scale it up. But probably because human beings, our language is connected to our models of the world, and so we have a lot of biases. I read this paper by DeepMind recently where they also try to integrate something like narrative consistency into generated text. So what you just said, like you have a certain person in a certain scene, and then obviously that person will remain constant across the scene, for example. This is something that's completely obvious to human beings, but like if you just train a transformer model
Mm.
that won't necessarily know that that's something that makes text much more realistic if you have that consistency. And then probably humans, we
Mm.
encode a couple of important aspects of when we read a very long text, we extract kind of like maybe the main characters of a book, something like that. And we extract that, store it into long-term memory, and then
Yeah.
we get kind of an idea of the book. And that's why we can like maybe extract features sparsely on large cop, like a very long text, and then train the transformer. I don't know if there are approaches like that. Probably there
Yeah.
are.
Yeah, there is a bunch of tricks that are being used to improve this. But this field is extremely new. Like probably there were no tricks a year ago, and now there are five candidates
Yeah.
that are being implemented.
Yeah.
But in engineering, we get things always a bit delayed because it has to be stable and prove to
Yeah.
actually work. Um, so I haven't really used any of these. I'm still using the original transformers, and we have this limitation
Yeah.
on
But it's
memory.
cool to go back to like the beginnings of Markov. When he came up with Markov chains, he did that by counting like letters in a Russian poem. And it's like at the foundation, you have this assumption that language is non-random and there's some meaningful structure in it. And you can also think of language as this hierarchy of patterns like symbols and words and sentences and maybe idioms. And then you can kind of find some meaningful like probability structure. This word should probably follow that word, and this letter should follow that letter. And then you already have these um, kind of meaningful structure. If you count up the letters, then you can probably distinguish between Russian and English and German text just by looking at the transition
Mhm.
probabilities between different letters. But if you want to like realistically build a language model, then you need to, yeah, either like the tree of transitions grows exponentially or it grows horribly, and even with context, it just
Yeah.
gets worse and worse.
Well, correct me if I'm wrong, but if this language model was a pure Markov process or Markov model, it would get us context just the word before the one I'm trying to predict, right? So it would be
Yeah, I mean, you
terrible.
can build a Markov model with different levels of context. I guess you can take like
Yeah,
two
then
words transitioning to two other words, for example, or one word transitioning to the next two words. But then you have a probability assigned to
yeah.
every combination of them, and that just means it just gets.
Yeah, then in that sense, a transformer model is a Markov process indeed, like because it outputs the prediction. Let's say I want to predict a whole paragraph. It's gonna predict one word, and then it will get that word as input plus the context and predict the next one. Then it's gonna get those two words as input plus the context and predict the third one, and so on. So it's a Markov process with context to generate this probability.
Yeah, probably essentially they are all Markov processes, but the with a like a naive Markov process, you just have like an example data set, and then you just count all instances of that word following the next word, and then you don't have like discover any meaningful substructure. And I think the self-attention mechanism discovers useful patterns between words, and then you have shared weights, and you don't need infinite amounts of parameters
Yeah.
to do that, but kind of discovers what context is relevant in which other context. Yeah, do you do we want to talk about self-attention or what it is?
Well, self attention, I'm not an expert in it, but I can give you kind of
Yeah,
an idea. Um, so before we had these language models, we had these work to back embeddings, which they give you a vector or embedding that contains information about the meaning of the word. And the big innovation of transformer models is that add um, they add more meaning into those vectors. For example, they add a positional encoding. So where in the sentence did that word appear? Um, but they also add a self-attention component. So um, if the word bank appears near the word sitting, then those two words have a really high self-attention because bank in the context of sitting has a meaning, right? Whereas bank in the context of money has a different meaning. So the self attention between bank and these two other words in a sentence will be really high, whereas the self attention with bank and the word drinking, it's gonna be very low, right? Because drinking doesn't tell you anything about the meaning of the word bank. Um, and self attention is something that the model learns. Um, so if two words appear in the same context, then it uses this self attention layer to add another component into this embedding. So in the end, this embedding is just a sum of different sources, right? You have the word embeddings that are pre-trained, you have the positional embedding, and you have the self-attention embedding. It just adds them up and uses them um, farther in the model, but that's the
yeah.
basic.
Then you can use several attention heads and basically scale up the model pretty efficiently, and you can
Hmm.
yeah, you can basically parallelize that computation because it's just a dot product over all like words in that
Yeah.
sentence.
Yeah, because like you usually put multiple attention heads because a word can have multiple dimensions of meaning, right? Bank can have its hard meaning about what kind of object or place is this, but it can also have meanings like a connotation if it's a happy place or not. So it might appear in a conversation about happy things or um, all sorts of different nuanced meanings. So that's why usually we put more heads and then they compete with each other. So you have a chance that they will not learn the same thing. Um, and in that way, they just improve the amount of meaning you put in that embedding.
Yeah. And then there was this famous paper, Attention is All You Need, which claimed, and it seems they definitely had reason for their claim that attention is really extremely powerful when it comes to building these language models. And the self attention mechanism
Yeah.
used in a relatively simple architecture.
Yeah, indeed. I think eventually they dropped the positional embeddings. That's why they say attention is all you need. Because they thought, and that's what the recurrent neural net models were based on. Like before transformers, we were using RNNs to make language models because you cannot use word embeddings directly because they don't have context. So they used language models, and the assumption there was that the meaning you are gonna be able to extract the meaning of a word by looking at the ones before it. So it's very dependent on the position of that word. And the first generation of transformers also had a positional embedding where they just feed some cosine function of where in the um, sentence the word appeared. Eventually, they discovered that the model can just learn that. I'm not exactly sure how it's done, but it might be the reason why they call the paper like that.
Yeah, I'm also not sure. I thought positional encodings were still used, but um, I don't know too much about that. Like, why do you think language models will come in or become important in the next couple of years?
Well, I guess first of all, like we talked before, our conscious thought is mostly made through language, or at least is the way we communicate. So if we can use AI to process language and produce language, then it's a way we can easily interact with machines. And in what ways? For example, summarizing the content of a page, so I can quickly decide if it's worth to read it. That's a very useful application, and it's currently there in some messaging apps where if you have, I don't know, 100 new messages, it produces a summary automatically, and then you don't have to read them if it seems uninteresting. Um, it's also improving a lot the way we search. And for example, I think search until now didn't use, or like we didn't have language models. So how did search know that the content of a page is relevant to what you're searching? And that's why they invented PageRank. So a page is interesting if it's linked to other pages around that topic and so on. So most of the search is most likely not about the content, but about the way users interacted with that page. Language models instead gives you this opportunity to process the content into something meaningful that you can use to rank if that page is interesting or not. I'm not really, I don't really know how they do it exactly, but that could be like a very big application. Um, yeah, like understanding natural text and being able to communicate with an assistant, for example. Until now we have these assistants which are becoming increasingly useful, but I personally don't use them. I don't find them too too convenient,
Yeah,
uh, instead of doing it myself. But for sure language models are going to solve this eventually. um,
yeah. But I think usually there's just this phase shift of a thing works and then, or it doesn't work, and then suddenly you change one thing and then it works so well that people just start adopting it.
yeah. um,
I think especially with AI, you have this. If you generate images, for example, like when we had generative models in the beginning with variation autoencoders, you could generate kind of realistic looking faces, but they looked a bit stupid still. And as soon
yeah.
as
Yeah, I mean, another application is the one you were mentioning,
yeah,
right? These diffusion models where you can
mm,
feed a sentence and they know um, what to reconstruct. Eventually, you're going to have diffusion models that do way more than just a picture, right? You could describe the kind of movie you want to watch and it could generate the movie.
yeah,
Um,
I mean, that's like an interesting topic in its own right. How to like, or what Jan LeCun also talks about frequently, how to get to the continuous domain.
yeah. I think one of my favorite TV series is Westworld.
Mhm.
And the thing I really like there is that they program the robots by writing the narrative of their life,
Mm.
and then the robot will acquire that personality, right? So the programmer of the robot is actually a novelist, um,
Yeah.
that writes down storylines. So they put these robots in a park and they become part of some amusement scheme. um, Yeah, like eventually you're gonna have language models that can understand description so well that they can generate systems like code, movies, anything that humans produce, basically.
Yeah, that's a very important point. I mean, Lex Friedman talks about robot human interaction a lot. And I think currently we don't have robots where that is really relevant, but like down the line, we can expect there to be ever more powerful um, yeah,
Mm.
intelligences, and us interfacing with them will probably happen through language primarily. So having powerful language models is also like our way
Yeah.
to speak to them. Like even with DALL-E, it's so amazing because you just plug in a sentence and you have like a picture in your mind of what it could look like, but it's really like yeah, pulling the algorithm to the level of
I'm pretty sure in a few years it's gonna be very impressive that you could generate a picture out of a sentence. We will be generating movies out of
yeah.
of a book, basically.
Yeah, that's. I think that's so amazing because it feels so special right now, but it will, like the Snapchat filter or something. I think in the beginning everyone was amazing. Oh, it can do facial recognition, but now it seems like
Yeah, now it's a given.
it's very commonplace. Yeah, but like or even like generating novels. I feel like with language models and these diffusion models and generative models, I think yeah, moving from like simple GANs and autoencoders 5, 6, 7 years ago, from like being able to generate at least realistic looking faces, but you trained with just thousands or millions of pictures of realistic looking faces, but now to this complete out of training set generalization of these concepts and combining it with language. I think that's pretty amazing. Or it gets much closer to what our human imagination is doing, for
Yeah, I
example.
agree. Also, these diffusion models work extremely different from the other kinds of models that we were used to use, where we one shot generate the output. Um, I think it's extremely interesting, also super new, so people hard to say where we can go with this. Um, Maybe eventually all of AI will move into diffusion models.
Yeah, can we quickly go into how they work? I kind of know how they work, but can we try
I also
to
kind of know.
we can try together. Yeah.
I mean, the quick explanation is that they take some input that you would like to reconstruct, like an image, and then you learn a model, a diffusion model, which means that you diffuse the image, and the model has to learn how to undiffuse it. So if you do it multiple times until you get pure noise, somehow the model can get that pure noise and also apply it multiple times to eventually get something out that looks like the image that came in. Um, how exactly that works, I think probably nobody can really answer that question, because basically what you're doing, you're getting a glass of water and dropping a drop of ink in there, and you're stirring it, right, until you get colored water. And then this diffusion model learns how to unsteer it until you get the drop back out of the water. Um, so it's, yeah, physically is impossible, but in the information domain, somehow we can reduce entropy by giving context.
Yeah, you have this noising process and you just add noise. Like you have 1000 time steps, for example, in which you consecutively add noise that distorts it slightly, and you learn the backward transformation. And then once you have learned
Mhm.
that in a general sense for a lot of images, you can just start from a random noisy image and then transform that into something that looks like something meaningful. And then with these language,
Yeah,
like with DALL-E, for example, when you have text input, you give that additionally during the like denoising process as information, what kind of image you want to generate. But in principle, you can also do it without text, and it's quite interesting that it works. I
yeah.
also don't have any intuition really.
I think it's quite similar actually to the thing we talked about before, where you can learn internal representations of an image just because the contents of it are conditioned or like patterned. So, for example, if I see an eye here, most likely there will be one nearby, and these kind of relationships. And if you have a model that learns the conditional probability of a pixel being there given the rest of pixels in an image, then it can start doing things like, okay, I have this very blurry or pixelated image, but this looks like a tree. So this pixel here I can break down into a leaf, bark, and bark. And then I can keep doing that. And just because it knows, okay, this is a tree, so I'm going to paint it like a tree, as I go more fine detailed, um, it will generate something
Yeah.
that looks like a tree eventually. So it gets context out of what it has already done in the
Yeah.
step before.
I mean, it bears some similarity to generative models that we already knew, like in autoencoders, for example.
Yeah, but basically it's the same concept applied like in a
Yeah.
many times.
Yeah. In GANs, you also just sample random noise basically and try to deform that noise
Yeah,
into a meaningful picture that then can fool the discriminator.
yeah, and then somebody found out that if instead of using as context the image itself, because this actually already existed before, it's called super resolution models, where you feed an image that has low resolution, and then somehow the model knows how to increase the resolution by painting details in those pixels. That already existed, right? So the only thing they added in diffusion models is they said, okay, let's do it like many times, and at the same time let's feed an extra context from a text and see what happens.
Yeah.
And then it can guide this upsampling process basically.
Right. Like, and denoising autoencoders also are
Yeah,
working in a similar direction. Yeah. It's quite like, yeah, I mean that what a lot of approaches, also these semi-supervised approaches and contrastive learning do is you take an image and you add noise, or you flip the colors, or you flip the image, or you crop something, or you make something missing.
yeah, or you make it smaller.
Yeah. Yeah, and then you kind of try to force the model to learn something meaningful that's not just learning by heart what's happening. It's kind of similar, probably, how humans as agents learn in the world, because we see things from different perspectives, and it's easier for us to kind of receive noisy input of certain things, because like my bottle of water is sitting on the table, but when it gets
Mhm.
dark, it automatically gets more noisy, my perception of that, and I extract like this kind of feature. Probably we
Yeah,
have to like force the input to through that noise to extract meaningful patterns.
yeah, I mean many times we do have like very fuzzy thoughts, or like you cannot decide what you have to do because you have too many things in your head, and then it becomes a step-by-step process of like sitting down and organizing your mind. I think it's very similar. You're kind of reducing the entropy of what's going on. um, and actually the other day I saw a new paper from diffusion models where they do that in latent representation. So I think the very costly thing of diffusion models is that they process the entire image in every step. So if you have a very big image that's gonna get processed 1,000 times, I think that's the amount of times they usually pass it through the model. And these models are huge, so it's extremely costly, right? If you can first encode this image into something that instead of a million numbers, it's just 500, and do this denoising process in there, then all of a sudden your model becomes a million times smaller or something like that. Um, and I saw a paper where they were trying that, and it actually works quite well. And I think we're getting closer at having a hint on what we do in our heads, because we also create these embeddings, and then what do we do with them? Denoise, tokenize. I think these kind of processes reflect in what we are inventing these days.
So like connecting that to this larger question of, can deep learning actually explain our intelligence by scaling up architectures, versus do we need completely new approaches? I think we are, like, in my opinion, we are moving, are we discovering certain aspects of deep learning that can actually guide us towards, yeah, like a better understanding of what we do in our head, as connecting to
Mhm.
what you just said.
Well, I mean, scaling is definitely not the only answer to it. For sure, it makes models better. But I don't feel like I'm a model, right? I do things in my head. Things change place, or yeah, I'm also reasoning, and any of these models we're talking about doesn't seem to reason at all. So I think creating general intelligence will be more of a process of finding either new processes like diffusion or tokenization or um, new processes that are interesting or relevant, and then how to connect them together. Like somebody found that if you get text to convert it to an embedding, then you get this denoising network, put them together, boom, you have a DALL-E. And that seems more intelligent than the models we had before. And we're just moving forward by putting pieces together rather than making them bigger, right? Um, so yeah. Um,
It also reminded me of JEPA, what we just discussed, like Jan LeCun's new paper on
mhm.
yeah steps toward autonomous intelligence or more general intelligence, and it's also about kind of a similar approach to representation learning, or kind of finding these energy functions over different
Mhm.
data modalities. But he's moving away from generative models in a sense, because he's claiming that they are too
Yeah.
costly and frequently not what we are interested in.
Yeah, well, he moves away from generative models in the sense that you don't output predictions of what you're going to observe. Instead, you just predict the latent representation of that future. Um, so you're still generating predictions, you just don't explicitly represent them. Um, I think, well, for the audience, JEPA means Joint Embedding Predictive Architecture. And it's called like that because um, you have two encoders that you're going to encode into a latent embedding, and you're going to try to predict how similar they are. Um, the thing is that between the first embedding and the second embedding, there is a predictor. So you're going to have the first embedding being converted into a prediction, and you're going to have that prediction trying to match the second embedding. So that's very useful, for example, to learn world models, where the first embedding is what I'm seeing, what I saw a second ago, and the second embedding is what I'm seeing now. And the predictor just learns this transition between um, just a dynamical model that transitions the latent embeddings. And then the objective is this energy model that tells you how similar is this prediction to what actually came in. So yeah, world models until now were telling you what's the next state that you're gonna see, and they were used to generate predictions, and then you would use these predictions to you would generate multiples of them, and then select the one that gives you the highest reward or the lowest free energy or whatever your agent is doing as an objective. Um, but that has the limitation that the future is a very diffuse process, right? You can have infinite futures, and they will even change with the actions that you make. So predicting the future directly is not a very efficient way to go about it. Um, Instead, what these models do is um, they predict a state, and they calculate the probability that it matches what comes in. And in this way, you're representing possible futures in terms of an energy, which is a scaled probability. Um, and you can actually represent the uncertainty on your prediction, which was not possible with predictive models. For instance, one of the tasks that we have in machine learning is to predict the next frames in a video, right? So using the current approaches, I would get the previous, let's say, 100 frames, and use them to in a convolutional neural net um, to generate the next frame and the next one, the next one, the next one, and it would come out with some output, which might or might not be correct. Problem is, as I was saying, that there are many possible futures. Which one came out um, is just chance. Instead, what you can do with JEPA, you don't predict futures, but you have a probability or something telling you how correct or incorrect that future is. And then you can use that with diffusion models to guide the process of generating a prediction. So instead of one shot predicting a future, you can give it a context in the realm of active inference. This would be a high level prior or a preference, and then I would iteratively generate that future. Um, and that's way more flexible because the model just has to learn how to compare a future, a predicted future with a preference, uh, rather than predict every possible future. So you have much smaller models. Um, and
Yeah. But maybe it's time to move on to like the final questions, because I'm also realizing that I don't have a lot of mental capacity. Do you have any favorite books or like papers on intelligence that you've read in recent years? I know we've read a couple of books in our shared book club, but
Yeah, it depends what you're interested on. If you're interested to learn about active inference, there's this one that came out by some of the people that actually invented the field. And the book came out a couple of months ago. It's called Active Inference, the free energy principle in mind, brain, and behavior. Um, that one is very interesting. It's also quite technical. And the thing in active inference is that we use really um, new or complicated vocabulary. So for me, it took a couple of years to get comfortable with it. Hopefully, this book will help the entry level for this. Um, but yeah, if you're interested in more in general how the brain, um, how consciousness comes appears in the brain, the book by Mark Solms that was in the podcast is extremely interesting as well. The Hidden Spring is called. If you want a softer introduction to active inference, there is the predictive mind, which talks about these hierarchies and how predictions come from the top down, and then from bottom up you have prediction errors coming, and how the system interacts. That is very non-technical and very interesting. Um, I think these three books are probably the main ones for me.
yeah, I think now it's time to wrap this up. There was a very in-depth and complicated, or like complex and in-depth conversation. So I think we are both pretty tired now. So thanks a lot for taking the time and for this great conversation.
Yeah, thank you, Manuel. I might even write stuff down that I came up with during our conversation. We should definitely continue discussing about these things.
Yeah, definitely. I think we will.